Welcome everyone.
Hi.
How's it going?
Good.
You having a fun time at MFG Day?
Yep.
Good, okay. So we're Behrend Robotics Club, and we're going to tell you a little bit about us first of all. My name is Ben Hollerman. I'm the treasurer of Behrend Robotics Club. We have 3 projects we mainly work on. We have our t-shirt tank up front, which we're going to be showing you a little bit later. We have our URC bot, which is shown in this cool CAD model right here. And we have our third project, which is Chalkbot, which you can't see. I can. Well, anyways, it's right behind here. It's just a little robot. So what you would do is you would draw it on an iPad. Draw whatever you want on an iPad, and then it can put that on chalk with 8 different colors of chalk. So that's our third robot. We're working on our URC robot. That's why it's just CAD right now, and our chalk bot. We're building that currently. But we have our t-shirt tank here to show you when we, like I said, showing you a little bit later. But next, I'm going to have Megan Swatner, our secretary, and our URC mechanical lead here to talk to you a little bit more.
Okay, so I'm to be trying to give everyone a glimpse into how we use the engineering design process, specifically using our gearboxes as an example. So to give a little summary of what we're going to talk about, we're going to go through the whole design process of determining our gear ratio and what our gears are going to look like, figuring out how we can achieve that ratio, figuring out materials, machining gears, and case hardening, eventually being able to assemble. So to go back to the beginning and explain in more detail, after setting up some of our parameters and doing a force analysis on a wheel, we selected a motor that fit our requirements, and then we were ready to start designing gearboxes. Initially, we looked at buying a gearbox online and just putting it on our motor, being ready to go. But since that didn't really fit our requirements, we wanted to have quite a bit of ground clearance since we are creating a Mars rover that has to traverse rough terrain. So if we just bought a gearbox, it'd be like very horizontal. So the motor would be at the end of the gearbox and it would just be flat like this. But since we wanted everything to be higher, we had our wheel input, motors went vertical. Our gearbox went vertical, and then our motors were up here. So it gave us a lot more ground clearance, which allowed us to traverse much rougher terrain. So we decided to design our own gear trains solely because it was not available commercially, and slightly because it's a little more fun that way. We figured out the number of teeth we required for each gear using gear ratios from our calculations, and then we had to choose our materials. So we chose a softer steel because we had to have it machined. So to make it accessible for a machinist, we had to do something a little softer. If you can see in that picture on my left, so or right, there's little divots on that gear. That's where we did our hardness testing, which we should have a little video of here. So we performed this test because hardness couldn't be completely determined from material properties. Hardness is a measure of like a local resistance, so just like on the surface of a material, the resistance there. So because we had our gears machined, we changed that surface. So we had to do a hardness test to determine what our hardness would be for our gears. And seeing as that hardness was not what we thought we needed from our calculations, we had to figure out a way to fix that. And that brings us to our case hardening. So case hardening is a process that increases the strength of a material and hardness, of course. So in case hardening, you pack a steel part in a layer of carbon and you put it in a furnace, get it really, really hot, and some of that carbon will infuse with the surface of the steel and increase the strength and hardness on the surface. So doing this allowed us to get hard, strong gear teeth that wouldn't break, but it also allowed us to have kind of a softer core that was more resistant to impact. You hit something really hard that's like really, really strong, a lot of times it's brittle, but stuff that's softer is more ductile. So we kind of got the best of both worlds, hard on the surface, soft on the inside. So We don't have any issues with fatigue or strength issues there. And after figuring out the entire process, we were ready to bake our gears. So we put our parts in for 8 hours at 1,700 degrees Fahrenheit. Removed the gears from a steel container that they were in, packed with carbon, reheated them, cooled them down, reheated them, cooled them down again. Eventually, we quenched them in water. So quenching is another process that can improve surface hardness and prevent defects that can eventually lead to cracking, just making sure we have a really nice surface finish. So after quenching the gears, we actually hardness tested them again to get our results, and we found that our gears were significantly harder than they were before the case hardening. So figuring out that our hardness requirement was now met, we were able to assemble our gear trains. You can see a picture of our CAD model on the left and our final assembled product on the right. So this process was entirely student-led, from figuring out all of our requirements and doing calculations to getting things machined and case hardening. So what we don't really talk about in this process is a lot of the calculations and math that go into each step. Throughout all of this, there's tons and tons of math. And also lots of hours on software like CAD and ANSYS software to prototype our designs and test them. So Anna's going to talk a little bit more about our software that we use there.
Hi, I'm Anna Carvalesco. I'm the publicity officer for Behrend Robotics, and I'm going to talk a little bit about the software that we do. And as you can see, as mechanical engineers, we do a lot of hands-on activities like Megan was talking about. But before we get into the nitty-gritty of actually building things, we have to use software to calculate, design, and test our projects. So this is MATLAB. We use this a lot for programming, for calculating data. Basically, you go in here and you can use it to solve simple things like algebra, all the way to differential equations and calculus. And you can also start plotting data and graph it for it to be analyzed. If you take this for a class, you hate MATLAB, but if you use this in your free time and as a hobbyist like robotics, you love MATLAB. MATLAB is your friend. And then, as Megan was talking about, we use ANSYS, and this is basically a software that analyzes different materials without us actually having to test it. Like, everybody has already tested it and done the results for different materials, where we can have it as a tool so we don't actually have to make a physical design and waste our time and energy. So as you can see from this I bar, we can see like the strength, toughness, deformation, which you can see a bending. And it also shows like thermal distribution. And if you get to like higher level classes, you can also test out your fluid flow systems and electromagnetism, which is pretty neat. On to our next program. This is Creo. This is a 3D CAD modeling software, which is computer-aided design. We can go into here and design parts, we can see the restraints of the parts, like sizes, measurements, how they fit together. We can build whole assemblies, see how much material is needed, and basically move the parts in different systems. And yeah, again, this just doesn't waste our time, and we can see how it's going to be as a final product. This is another CAD program, which is superiorly better. do not go in Creo. This is what Penn State uses and what the Behrend Robotics uses. It does 3D design too, 2D orthographic views, so you can print them out and show other people and actually communicate what you're building as an engineer. You can also simulate things and like element analysis as before. And now that we have our projects calculated, designed, and tested digitally, we can go into the actual making of our parts, and we'll get into that with Ben.
Thank you, thank you. So with 3D printing, there's this idea called iterative design. So with iterative design, you try it again and again and again, and eventually it works. So I have 3 different parts here, and one of them works for what I'm trying to do. This is actually going to be a mount for a motor controller. On a show of hands, who thinks it's the first one that's going to work? No. How about the second one? No. The third one? You're right, you're right. It is the third one. They're printed in different colors of plastic just so I could see which one it ended up being. But yes, you're right, it is the third one. So if you go ahead, you can see actually that in use. So this is the motor controller that controls some of our motors on our URC robot, which we're currently making. And so in being able to make it connect to the box that we needed to connect to is really cool. And the 2 previous designs that we had didn't work, but this one did. So being able to try that again and again. And in 3D printing, we use Inventor to 3D print, but has anyone used Inventor before, heard of that? How about Tinkercad? Yeah. Have people used the 3D printers before? Yeah, a few here and there. So they're really helpful. You use them in possibly middle school, maybe high school. They're especially useful in college where we're able to do that iterative design. We make prototypes of different things that we need to do. So this was also for the URC project. This was modeling out this design of this bracket before we put it into steel. The next thing is looking at just being able to visualize in actual space and touch. This is our URC robot chassis, being able to look and say, okay, well, the wheels are going to be there. We're making that type of bar there, and we're doing this. Just being able to see in actual real life is a real opportunity for 3D printing. And even with 3D printing, you can use it in any different type of thing. Use it in robotics. A lot of you have used it before, and you can also use it in hobby projects as well. So even when things don't work very well, like when this happens, we know that we can always go back and we can print it again. We can look at it and say, okay, how can we make this better? How can we make this print better and work better? So next, introducing the wheel. So we are one of the things that we 3D printed. So our president, Adam Satchridge.
Hey everybody, I'm Adam, and I'm going to tell you how we spent the better part of a year reinventing the wheel. So for our rover project we needed wheels so that we could drive the rover. So some of the requirements for our wheel is it had to be able to support a 110-pound rover. So between the 6 wheels, it would have to be able to handle that amount of weight. The wheels would have to survive a 2-foot drop. So part of the competition is off-roading. So there might be times we go up a little ledge and the wheel has to not break when the weight of the rover falls on it. We also have to have traction on various surfaces. So we're in the desert, so we're going to be going over sand, gravel. We could be on pavement depending on where we're testing. So whatever wheel we designed, we wanted it to have good traction. And our third requirement was we wanted enough ground clearance. So having little tiny wheels, we might be scraping the bottom of it depending on how we designed the rest of the rover. So it's something we wanted to keep in mind throughout the process. So our first design was this wheel. So it's a 10-inch wheel. It was made of ABS, which is a hard plastic, and it was completely 3D printed. So we decided to 3D print our wheel because we were looking online to find a good solution for what we wanted, but none of the wheels really met our requirements, and making it ourselves would also be fun. So this is the first design. It had a 10-inch diameter, and we thought it'd be good, but during initial testing, we realized some issues. So to test the wheel that it could survive the 2-foot drop, we put a metal bar through the center, loaded it with weight, and dropped the wheel from 2 feet. The wheel cracked. So we knew it wouldn't survive the drop test, but we decided to modify the design to see what we could do to change it. So on the left here, you can see a simulation we did of impact and ANSYS to see from what height would the wheel survive. So we're looking at where the stress built up in this wheel and where it's going to break. So from trying that multiple times, we realized no matter how we designed a wheel out of this plastic, it was not going to survive the drug test. So this led us to, here's a summary of the issues with our design. So it was too big. So even though we wanted the ground clearance, we did realize that this big of a wheel, we had to use a larger printer, which had more issues. And it also was becoming too heavy. So we're limited in how much weight we can have on the rover. So we really don't want heavy wheels. The wheel had no impact resistance. And the inside of the wheel that took the force from the shaft and transmitted it would spin out. So the plastic wasn't strong enough in that area. So we needed to solve these problems. So this led us to a new design. So instead of using a rigid plastic, we decided to use a more flexible plastic, TPU, that behaved more like a rubber. So here you see us designing a concentric hexagon design of a wheel. So no matter which way you squish this wheel from, is going to be equal amount of squish. And on the next slide, you can really see the durability that this new material had. So on the left, we're crushing with a vise. On the right, we're throwing it at the floor. That was not the only instance of us throwing it at the floor. We really tried to break this wheel. We could not get it to break. So this new design was looking pretty promising, but it wasn't without issues. So it was difficult to print this plastic. So this material was harder to manufacture than our more rigid plastic. So because of that, we had to use a higher quality printer, which meant we had less space to build with it. So our better quality printer had a smaller print bed, so we had to make the wheel smaller. The hexagon design we had was also very difficult to model. So Anna was talking to you about all that CAD software. If we were to do it by hand in that CAD software, it took us about 2 hours to make changes to the wheel, just because of how everything was like designed. Third issue was the inside of the wheel was now basically made out of rubber. So the shaft, when you spun it, would just easily slip. So there's no way you could properly get the torque from your gearbox to the wheel. And the wheel also went to buckle when the load was applied. So at the end of the Vice video that wasn't there, when you squish it, it just bends in half like a potato chip. So we had to solve those issues, but we thought they were something we could solve. So to get around the first issue of it being difficult to design, we wrote a program in Autodesk Inventor using VBA, where you gave it the parameters of the wheel you wanted. So the size of the wheel, how many hexagons you wanted, thickness, the radius, all of that. And it took all those numbers and automatically built it in Inventor. And then we could take that design in 3D print. So writing the code for this took a couple days, which was longer than just designing the wheel on its own. But after we had this, within a couple of minutes, we were able to make over a dozen designs of the wheel. So we could see how different settings would change different properties of the wheel. So sometimes investing more in the beginning of a project and putting the time in will help you later on. So sometimes good to make a specialized tool. The next issue we had to solve was the torque transfer of the wheel. So instead of our solution was, instead of having the shafts go directly into the wheel, have the shaft attached to a metal plate that attached to the wheel. So here you see some of that design process. So in the top left, we have the simulations we did on the plates to see how thick we need to make them. We decided to make the plates out of steel. We knew plastic wasn't really going to work out well, and steel can be designed for infinite life, so that no matter how long these wheels are going, the steel plates will be intact. So on the left, we have the simulation. Down here is some of our initial testing. So this blue string is attached to a bucket of sand, and we're trying to see how much weight we can put on these plates before the shaft spins out. Using this testing, we were able to see that this model was correct, which led us to that final design. And this is the final design of the wheel. We made it wider so it doesn't buckle. We got the hexagon density just right by doing multiple tries with that program we wrote. And this metal plate in the center is plenty strong to transmit the power from the motor. So I'm going to pass this around if anyone wants to just squish it. It's kind of see what we ended up getting. So the wheel itself is made of TPU, and that plate in the center is made of steel. And now I will be introducing what you see in front of you, which is the t-shirt launching robot. So this project has been in the works for about 4 years now. We had a club member a couple of years ago decide they wanted to do just a fun project. We used to do just BattleBots then, and he wanted something else to work on. So in his free time, he started designing this in CAD, and over the course of the past couple of years, it came into reality. So it has 6 barrels that each revolve using an indexing mechanism that Dalton will talk to you about in a bit. And the launching power is by 2 air tanks. So it has a primary air tank that is a welding tank at 3000 PSI, and then a secondary steel tank that is charged to 100 PSI. So Dalton is going to tell you a bit about our process we use to design the indexing mechanism.
Hello, I am Dalton. I'm the team lead for T-shirt Tank over here. So this lovely thing that Adam was calling the indexing mechanism right there is called a Geneva drive. Now Geneva drive works is, as you may or may not be showing you, the round disc spins and that shoulder bolt grabs the star and rotates the barrel. So now instead of having to constantly run the motor and then getting it exactly right, we have that star that gets it to an exact point where we can line up the barrel and we have as much pressure as we can launch it through. So our air system, as Adam was talking about, is 3,000 PSI in that big middle tank, and then 100 in that side tank that he's not going to show you. So I can. So some future plans. Hoping maybe to put some tracks on it, because as of right now, as you probably just watched him do, it doesn't work all that well on surfaces like this or like taller grass. It only works on concrete and turf, which isn't really useful if you want to take to, like, let's say a soccer game or something, shoot it into the stands. You have to be able to turn it. As well as a better solenoid, which is the part where the black bit is by the air tank that allows it to actually regulate the pressure. We want to make it up to 300 PSI so we can launch it even further. And then as well, we want to work on water cooling for the motors. Because as of right now, the motors tend to like to overheat, which is really not an issue, or really not a good thing for keeping motors alive in the long term. So now we're going to launch some t-shirts for you guys.
Okay. Everyone like back up in the room. About like middle of the back of the room. I'm gonna try to get this.